Thanks, Franco, for that introduction. As you can see, I'm not a co-author on this work, but I'm a senior researcher in the group of Robert Flatt at ETH Zurich. And I happened to be in the U.S. For a conference last week, and for the purposes of sustainability. I had a talk also in Switzerland, and Robert and I flip-flop talks. So, with that caveat, the work I'll be presenting here has to do, as Franco mentioned, with chemical admixtures for blended cements. Primarily the work of the PhD student here, Siraj Mughal, and as you can see, also Franco's a co-author. To start off, I'll give you a little background on superplasticizers, why we use them, how they work, and in general, when we're talking about superplasticizers, we're talking about workability, right? We love concrete because it's a material, of course, for its hardened properties that we treasure, but we also treasure it because we can work it and get into the shape that we need, and so that's where workability comes into focus. And when we talk about workability, we talk about rheology, the science of deformation, and when we talk about rheology, we really are talking about yield stress in the context of concrete. So as concrete is can be really understood to be a series of suspensions of solid material in a fluid medium, the really controlling factor of our yield stress is at the cement paste level. We're talking about cement particles suspended in water, and at this level, the particles can exert an interparticle force on each other, an attractive force on each other, and form this network like you see here. And when we talk about yield stress, we're essentially talking about a solid-liquid phase transition, as illustrated by this cartoon, where there's a minimum shear stress that you've got to apply to break this interparticle network. So as you can imagine, the volume content of solids plays a major role in your yield stress, but also things that modify the interparticle forces, including polymers, which can adsorb to the surface of our cement particles. So if we take a polymer, a typical comb-shaped superplasticizer, it's got a backbone, that's the blue, charged so that it can affiliate to the surface of our particle, and side chains that stick out like a comb, hence the name comb-shaped superplasticizer. They are floating around in solution, they're attracted to the cement particle, they operate by adsorbing to the surface of the cement particle. They adopt a particular conformation, which Robert produced a model some years ago to predict the amount of surface coverage that you can get with given molecular parameters for a polycarboxylate ether superplasticizer. And they modify the interparticle forces through something called steric repulsion. Essentially, the steric repulsion means that atoms can't occupy the same space, so they essentially push the particles apart. The attractive force between the particles, it follows an inverse square law. So it doesn't really take that much to push them apart to modify the interparticle force significantly. And to give you a sense of the relative sizes we're dealing with here, this is a Swiss footballer. The hairs on his head are akin to roughly the surface thickness of the polymer on the cement particles. Now, what the polymers do to change the interparticle forces is dependent on a couple of things. It's dependent on surface coverage as well as the thickness of the particle. So first you've got to cover the surface, like you have this beach here. You want to cover the surface of this beach with shade first, and at that stage, with the analogy of the particles, the actual just surface coverage is key, so the affinity of the particle to the surface is important, and essentially what that comes down to is the charge of the backbone to stick to the surface of the charged particle. Once it gets covered, then conformation starts to become a big deal, and the actual side chains and the layer thickness becomes the key. And typically, we're in the range of surface coverage control, is my understanding. Now, with blended cements, things start to become much more complicated because we're no longer dealing with sticking this superplasticizer to the surface of our clinker surfaces. Now we have other things like limestone, calcined clay, and other supplementary cementitious materials. This talk is going to be about LC3, so I'll be focusing on these three surfaces. And then you also have surfaces that are growing, hydration reactions that are occurring and forming things like ettringite or other hydrates that can occur in the early ages. And where this superplasticizer is going is a major question and a focus of the work, a lot of the work which is in the group for the past three years or so, and especially how it changes with time. Now, what that means then for LC3s is what I'll get into now. And the problem with some LC3s, LC3 is quite variable because of the calcined clays are coming from quite variable sources, and some of these, as we know, can lead to workability problems, and it's illustrated here. Taking the same, first of all, these are the same initial fluidities, the same initial yield stresses for LC3 and OPC systems. One of the things you'll note is the higher content of superplasticizer needed for the LC3 system because of the higher specific surface area, presumably. You can see that the flow is lost much, much faster with LC3 compared to OPC. So this is the increase in the yield stress over time. Schematically, if you look at it on the y-axis, you have the yield stress, the x-axis time. Typically, what happens with OPCs is you have a given yield stress, and then at a certain time, the yield stress starts to increase. This is our flow retention time when that starts taking off. You can add a little bit more superplasticizer initially, lower the initial yield stress, and then get a corresponding increase in your flow retention time, and so on. So there's this essentially corresponding increase with flow retention time with a decrease in yield stress. There's a limit on it where you'll cause segregation and an unstable suspension, so you can't do it forever. The difference with LC3, so I just really wanted to highlight that lower yield stress, increase in flow retention time, so increased PCE, increased flow retention time. With LC3, you have to add a little bit more PCE in the beginning, a little bit more superplasticizer, but the flow retention time is shorter, and regardless of how much you add to lower that initial yield stress, your flow retention time is still not improved, even below the segregation limit. Essentially, what a lot of people are doing in dealing with LC3s is to add a lot of higher initial PCE to take care of all that additional surface area. You know, it's a little bit of extra cost, but that's how you deal with it. However, you still end up with this flow retention problem. So the question is, how do we get to something like this? The first step that Suraj took was to try to do some experiments to explain flow loss. What's the mechanism that causes LC3 to lose fluidity? And the experiment he did was adding PCE in the mixing water, adding the cement, mixing it up, and then he went either one of two directions with it: flow loss compensation or no flow loss compensation. The flow loss compensation, essentially, as you start losing flow, then you would redose more PCE to get back to your initial fluidity and mix it up, get your fluidity back. On the case of the no flow loss compensation, or NFLC, he'd measure the specific surface area evolution over time. And in the case of both of these, then measure using TOC the amount of adsorbed polymer, and do this at regular time intervals. On the flow loss compensation was only done for LC3, and the NFLC for OPC and LC3 systems to get this proper comparison. So how the specific surface area evolve? So this is for OPC, and this is for the non-flow loss compensated LC3. And while they look similar, take a look at the scales. On the left is OPC, on the right is LC3, and you can see it's a 4x increase in the specific surface area roughly for the LC3 in the same amount of time. So not only is there higher initial specific surface area, it's also massively increasing. It's a higher growth rate over time. If you look at the amount of adsorbed polymer in the OPC system, it's increasing over time. In the case of the flow or non-flow loss compensated LC3, there's a marginal increase in the amount that's absorbed over time. And in the case of the flow loss compensated, it also follows an increase in time of adsorbed polymer, because as you're adding more polymer. So this is showing, again, just drawing some lines through the previous plot, showing the growth in the specific surface area over time with a 4 or 5x increase, and highlighting, of course, here the higher initial specific surface area as well as the higher growth rate. These are for the non-flow loss compensated ones. If you draw lines through the amount of adsorbed polymer, you can see that some outliers were removed to be able to get roughly the same initial amount seen here, but there's an order of magnitude difference in how much polymer is being adsorbed in the flow loss compensated versus the not flow loss compensated LC3s, and even the amount that's being adsorbed over time for the non-flow loss compensated LC3 is lower compared to the OPC. This is an indication that you just don't have a lot of polymer floating around in the solution. A lot of it's just consumed initially. So if you plot the change in the amount of polymer adsorbed versus the change in the specific surface area, for OPC it's increasing. As you get more surface area, you get more polymer adsorbed, and this cartoon kind of illustrates the hypothesis behind that. You have our clinker particle here. The red combs are our high charge density, so these are polydisperse polymer systems. High charge densities will adsorb onto your cement particles. The greens are the lower charge density on the backbone. They're going to be floating around in solution, and as you grow more surface area, it's represented by these ettringite needles, just as a model. It's not necessarily ettringite, it can be other surfaces that are being formed. But these are then consuming the free polymer in the solution. In the case of non-flow loss compensated LC3, the hypothesis is just that there is not a lot of free polymer floating around in the solution. And then as you form more specific surface area, the particle, the high charge polymers, or the polymers adsorbed on cement or clinker particles, will then migrate to the new surface area, and that's the source of your flow loss, at least according to this hypothesis. And in the case of flow loss compensation, as you're adding more polymer, it's adsorbing to the newly formed surface area. And if you plot a straight line through these results, you can see that the OPC and the flow loss compensated LC3s are falling roughly on the same line. And as it turns out, the slope of this line can be closely predicted by the model developed by Robert some years ago. In the model calculation, at least from what I read in the submitted paper, so it's still in review, is something like 0.32 or 33. So it's a pretty close prediction, indicating that there's fairly good surface coverage on the surfaces that are being formed in LC3. All this to say that essentially it seems that the evidence indicates that it's the newly formed, rapidly forming specific surface area in LC3 which is responsible for the flow loss. So when it comes to a pragmatic solution for it, there's a couple of directions you can take. On the one hand, you can add a polymer that doesn't adsorb initially but has a stronger affinity for the new surfaces that you are forming. But this doesn't attack the issue at its root and potentially can require quite high dosages. So an alternative approach, which I'll show here, is to block the initial reactivity to prevent the formation of all this surface area from the outset. PCEs don't seem to be very good at this, but in the context of a student project a year ago that Suraj supervised, they looked at some other chemical structures that might do this, in particular the diphosphonate superplasticizers. So this is what the what a PCE looks like schematically, and a diphosphonate looks like this. And the diphosphonates operate on a similar principle. They operate based on steric hindrance, but they are single chains. So that's the chain of the diphosphonate there on the bottom, analogous to the PCE side chain as well. But as they're single chains, so they're like, instead of a comb copolymer, they're just like a single tooth of a comb. They are strongly retarding and have been a specialty product for oil well cements until now. In the context of this project, they found that 0.4% was a little bit too low, and that you got segregation at 0.7%, just to get lower and upper ranges to test things out. Using 0.5 and 0.6, you can see that 0.6% actually looks pretty good, but 0.5% is probably also a good compromise. So you get the low initial yield stress that you need and the flow retention that you need as well. The problem with it is that there's excessive retardation that occurs, as you can see in these calorimetry curves. And so what they looked at was this combination of PCE and diphosphonate together. In other words, to use the PCE, where they're trying to replicate these curves, and the idea is to use the PCE to drop your initial yield stress down to what you need, and then the diphosphonate is going to take over to be able to give you the flow retention that you need. You can see they got pretty good matching results from these LC3 and combination of PCE systems. Now, a significant question behind this is exactly where and how these superplasticizers are doing this. What are the phases which are responsible for the increase in specific surface area? Maybe it's the amorphous phases in the calcine clays, for example, and how this evolves over time. This is work to come. So to conclude, it seems that I think a takeaway that we'll take from this is that the rapid formation of additional surfaces is responsible really directly for the flow loss of superplasticized LC3s. I didn't show any of the evidence here, it's in the submitted paper, but evidently side chain intercalation does not play a major role. Covering these surfaces is what compensates flow loss with polymers that you can add later or can have a delayed absorption, potentially with a low dosage response, but it seems like blocking the early reactivity is quite promising with the diphosphonates. It's a different class of superplasticizers. And again, it's really coming down to getting that right combination to get your lower initial fluidity as well as the flow retention that you need. So with that, I'll do my best to answer your questions. I probably talked a little too long.